Welcome, friends. Today we'll discuss about the X-ray diffraction, and in this chapter we are going to discuss the concept of reciprocal lattice, which was introduced by the scientist P.P. Ewald in 1921. The concept of reciprocal lattice is very much important when you are studying the different types of X-ray diffraction methods. In the chapter, we'll discuss the Bragg's law for X-ray diffraction also, and we'll see the X-ray diffraction methods like Lau method, rotating crystal method, and powder photograph method. All these things we'll be discussing in the chapter. So, in this first lecture, we will discuss the concept of reciprocal lattice, and we will see how to construct the reciprocal lattice from a direct lattice. And today we will discuss the construction of one-dimensional reciprocal lattice. In the next lecture, we will discuss the construction of two-dimensional reciprocal lattice, and we'll extend the same to the three-dimensional. Now we know that in crystal the atoms are arranged in regular and periodic three-dimensional geometric pattern, and because of the regular and periodic arrangement of atoms, we can imagine a large number of crystal planes, which we call them as atomic planes also. And all these planes are large in number and they intersect each other. And to visualize or to represent such a crystal planes, we know that the scientist Miller has introduced a method in which he has introduced three numbers corresponding to three axes, and these three numbers are HKL and they are called as Miller indices. So Miller indices, they are used to represent the crystal plane that we have discussed in my earlier lecture. Now we'll discuss how to construct the reciprocal lattice. Now the basic idea of the reciprocal lattice is that a two-dimensional plane can be represented by a single line, uh, which is normal to the crystal planes. So this is the basic idea regarding the construction of the reciprocal lattice. Means two-dimensional plane is represented by a single line which is normal to the crystal planes. Means we have to reduce the one dimension, and two-dimensional plane is represented by a single line, and it is now becomes simple to represent the crystal lattice. It is called as the reciprocal lattice. Now we will see a very basic thing or very simple thing to represent the one-dimensional crystal lattice. So there are two to three easy steps to construct the reciprocal lattice. What are those three steps? The three steps are: first is from common point, which is taken as origin. We have to draw the normal to the every family of parallel planes in the direct lattice. Means whatever there are sets of parallel planes, to all these sets of parallel planes we have to draw a normal, we have to erect a normal from a common point, which we call it as a origin. A simple step, first step. Then we have to take the length of each normal, which is equal to the reciprocal of the interplanar spacing corresponding to that particular set of parallel planes. Means particular or each set of parallel planes will have a particular interplanar spacing, and we know that the interplanar spacing depends upon the Miller indices, and we have to draw the length of the normal, which is equal to the reciprocal of the interplanar spacing corresponding to that set of parallel planes. This is this is the second simple step. And last step is we have to place a point, we have to place a point at the end of each normal. Means we have to put the point at the end of each normal, and that point is called as reciprocal lattice point. So this is a very simple method to represent a two-dimensional plane in terms of a single normal. Now, by constructing such a reciprocal lattice points, you will get all information about the crystal that we can get in direct lattice. Means you will able to know what is the Miller indices, what is the interplanar spacing, all these things that you can get by constructing this reciprocal lattice. Now we'll see how one-dimensional reciprocal lattice can be constructed. For that, consider a three-axis. Suppose these are the three axes. Suppose this is the axis A. This is the axis A. Suppose this is the B axis and this is the C axis. These three axes are not necessarily perpendicular to each other. These are not rectangular axes. So they are oriented with respect to each other with different angles. So suppose this is A axis, suppose this is the B axis, and suppose this is the C axis, and suppose O is the origin. Now we can consider 1, 0, 0 planes, means the planes having the Miller indices 1, 0, 0 planes that we'll consider. So that planes can be shown like this. Suppose these are the 1, 0, 0 planes, means uh, this plane is at a distance of 1a. So this distance is a, or distance between these two planes is again a. So these planes are situated at a distances of 1a, 2a, 3a, and all these planes are parallel planes, and all these planes will have Miller indices 1, 0, 0 like this. Now what we have to do, as we have discussed how to construct the reciprocal lattice. First of all, we have to draw a normal to the set of parallel planes. Means all these are parallel planes and we have to draw the normal, and that normal can be shown somewhat like this. Suppose this is the normal, and normal we have to draw, and second step is that we have to take the length of normal which is equal to the reciprocal of the interplanar spacing. So this particular plane will have interplanar spacing d1, 0, 0, and we have to draw the length of the normal. We have to take length of the normal which is equal to reciprocal of the interplanar spacing, means we have to take the reciprocal point at a distance of 1 upon d1, 0, 0. So that point can be drawn like this. So suppose this is the point. We have drawn OR1 is a reciprocal lattice vector, you can call it as, and we have taken the length ORN R1 is equal to 1 upon D1, 0, 0, and we have drawn the point R1 at the end of the normal, and that point is called as the reciprocal lattice point. So this is very simple method to construct the reciprocal lattice point. Now we can consider another reciprocal lattice points likewise, or this can be represented like this. You can show the reciprocal lattice point 1, 0 for 1, 0, 0 plane as OR1, and it is proportional to reciprocal of the interplanar spacing, means 1 upon D1, 0, 0. Taking the constant of proportionality 1, m, it is called as scale factor or magnification factor. We can write OR1 is equal to m into 1 upon D1, 0, 0, and generally the scale factor or magnification factor is 1, and therefore we can write OR1 is equal to 1 upon D1, 0, 0, and this 1 upon D1, 1, 0, 0 is the unit reciprocal lattice vector along a axis. It is also represented as D1, 0, 0 star. So like that one can construct the reciprocal lattice point in one dimension. Here we have to why we are calling it as one dimension, because the plane is parallel to remaining two axes. It is parallel to B axis and it is parallel to C axis. It is not making intercepts along B axis and C axis. That's why it is called as the one dimensional reciprocal lattice. It makes only intercept only along A axis. So that is how you can construct the reciprocal lattice point in one dimension. Now there are other planes also. You may consider the plane at the midway between the planes having Miller indices 1, 0, 0. So you can consider exactly at the midpoint the plane, and that plane will have Miller indices 2, 0, 0, because it will make intercept A by 2 along A axis, and by making the use of procedure to calculate the Miller indices, we can easily show that such planes will have Miller indices 2, 0, 0. Such planes can be represented like this. So these are the planes having Miller indices 2, 0, 0. They are exactly in between the planes having Miller indices 1, 0, 0. So this plane 2, 0, 0 is midway at this point, or you can have this 2, 0, 0 plane between these two planes having Miller indices 1, 0, 0. Now, obviously, these planes will be having interplanar spacing equal to D200, and it will be exactly half the interplanar spacing corresponding to planes D100. That means this distance is A by 2, and such planes will have interplanar spacing, which is half, means half of the interspanning spacing of 100. So it will be 100 divided by 2. That will be the interplanar spacing. Now, same procedure we have to follow. Means normal we have to erect, and we have to plot the point at a distance equal to a reciprocal of interplanar spacing corresponding to 200 planes. Means such a point will be showed like this. Suppose this point will be R2. Obviously, this point will be ahead to the point R1, because you can understood from this as uh, reciprocal lattice point 200 plane you can construct. That means OR2 is equal to 1 upon reciprocal of interplanar spacing corresponding to 200 plane, which is D100 divided by 2. So it will be twice the or 2 divided by D100, and we know that 1 upon D100 is nothing but unit reciprocal lattice vector, and therefore you can write this as OR2 is equal to 2A R2. 2A star means it will be exactly at a distance of twice O R1. So like that you can construct the second reciprocal lattice point. So this is very simple method to construct the reciprocal lattice point. Now you can also have the planes having Miller indices 300, means the plane lying at the distance of 1/3 from the origin, and such a plane will have interplanar spacing D100 divided by 3, and reciprocal lattice point corresponding to such a plane will be at a distance of 3A star. So likewise, in a very simple manner, you can construct the reciprocal lattice points as R1, R2, R3, here somewhere R3, R4, and so on. So all these reciprocal lattice points, they will be on the normal to the crystal planes, and it will not be necessary to represent the crystal in two-dimensional way, but you can represent crystals by the reciprocal lattice points. That means by one-dimensional line. So this method was introduced by PP evolved in 1921, and it is very useful to understood the concept of the X-ray diffraction by the crystals that we are going to discuss in next some articles. So similarly, the reciprocal lattice point for 300, 400, 500 planes can be represented as, for example, reciprocal lattice point for 300 planes will be OR3, and it will be equal to 1 upon D100 divided by 3, because interplanar spacing corresponding to 300 planes will be 100 divided by 3, and its reciprocal will be 1 upon D100 divided by 3. It will be 3 divided by D100 is equal to 3A star. Similarly, you can have the reciprocal lattice point for 400 planes as 4A star, and so on. So in general, we can write the reciprocal lattice point along A star axis. A star axis is the axis in the reciprocal lattice. So it is analogous to A axis. So that reciprocal lattice point along A star axis for planes having Miller indices in general H00 will be, we can write it as DH00 star. It is a vector. It is also represented as RH00 star, or sometimes it is also represented as sigma H00 star. So these are different letters used to represent the reciprocal lattice. So it is vector is equal to HA star. So in the similar way, you can consider the planes making intercepts along B axis and C axis, and similar method you can follow, and you can write the reciprocal lattice point along B star axis, uh, and the planes having Miller indices 0, K0, that reciprocal lattice point, it will be given as, or that vector will be given as D0K0, because it will be parallel to A and C axis. It will have only intercept along B axis. That's why that reciprocal lattice vector will be represented as D0K0 star is equal to, it is also represented as R0K0 star. It is also represented as sigma 0K0 star, and it will equal to KB star. In the similar way, you can write the reciprocal lattice point along C star axis, and those planes will have Miller indices as 0, 0, L, and such reciprocal lattice will be represented by D00 L star is equal to R00 L star, or you can call it as sigma 00 K star is equal to L C star. In this way, you can construct the reciprocal lattice in one dimension. If you have understood how to construct the reciprocal lattice in one dimension, you will be able to understood easily how to construct the reciprocal lattice in two dimension. So my next lecture will be dealing with the construction of reciprocal lattice in two dimension. Thank you for watching this lecture.